Welcome back, everyone. Today we'll learn how our agent can handle uncertainty. For our homework assignment, we'll send our agent on a treasure hunt under the sea. So far in this course, we have studied problem solving and search, and we have also covered logical reasoning and planning. In the remaining weeks, we'll focus on the tools that got us out of the AI winter. These tools include tools that allow us to deal with uncertainty and learning. So, we just finished talking about the knowledge based approaches. Remember, these approaches were initially very ambitious in wanting to represent all human knowledge and then use inference for decision making. However, these knowledge based approaches failed to deliver on their promises with the hardware limitations of the time. People lost confidence in AI, and this led us in the late 80s to the AI winter. The 90s saw a shift in the approach. Rather than using absolute logic, AI researchers focused on managing uncertainty. The computers were also becoming much more powerful, so we were actually able to solve more than toy problems. This led us to what some people call the AI spring. So, where does uncertainty come from? Uncertainty comes into play when the environment is partially observable. Partial observability may be due to incomplete knowledge. Our agent just does not know what's going on in the other room. Or it can also be due to faulty sensors, right? Our agent sensors are not perfect. And uncertainty can also come into play when the environment is non deterministic. So actions do not always go as planned. For instance, if our agent is swimming in the ocean, there could be waves and rip currents. So our agent may try to go in one direction but end up in a different place. And of course, the non determinism may also be due to faulty actuators. In the next couple of lectures, we'll introduce a framework for managing our beliefs and our knowledge. This knowledge is divided into three main categories. We have observed variables, these represent our evidence. We have unobserved variables, what we do not know directly, and we have our model. So the observed variables represent what our agent knows about the state of the world. These observed variables may be the sensor readings or the test results or the disease symptoms. Unobserved variables, on the other hand, represent things that we do not have direct knowledge of. Our agent needs to reason about these unobserved variables to make a decision or take some action. The agent needs to reason, for instance, about where the treasure is or what disease is present. Our model represents what we know about how the world works. The model tells us how the observed variables relate to the unobserved variables. Note that our agent can also learn the model. We'll be talking more about that in a couple of weeks. So for our next homework assignment, we'll have to guide our agent to a treasure hidden at the bottom of the ocean. Our agent has a sonar that helps him locate the treasure, but that sonar is not perfect. Sonar sensing is much cheaper than diving, so our agent gets to sense several locations to get a general idea of where the treasure is. After a few sonar readings, the agent has to make a decision as to where to dive for the treasure. So let's start in sonar mode and take a few sonar measurements. A green sonar reading means the treasure is probably far from this location. A yellow sonar reading means the treasure is probably closer, and the red sonar reading means the treasure is probably very close. We need a few measurements here to decide where should we dive. And at this point, I think we're ready to make a decision. So let's go ahead and dive. And here's our treasure. So in this case, our evidence, the observed variable, is the sonar reading at the sensing position. It's the green, yellow, or red that we sense. The unobserved variable is the location of the treasure. The model is our sensor model. It tells us how the evidence, the sonar color, relates to the position of the treasure. And this model is probabilistic. When the treasure is at the exact location we are sensing, so the Manhattan distance to the treasure is 0, there is a 70% chance that our sonar reading is red, and there is a 30% chance that our sonar reading is yellow. Now, when the treasure is 1 square away from the position we are sensing, there is a 30% chance that our sonar reading is red. There's a 60% chance that our sonar reading is yellow, and there's a 10% chance that our sonar reading is green. So a red does not necessarily give away the location of the treasure. But if we collect several readings and we use the probabilities given by our sonar model, we can get a pretty good idea of where to dive.